In our last video, we looked at the exponential growth or decay model. In this video, we're going to look at some special things called the doubling time and the half-life. Let's say that we have let's say an investment, and we know that we have deposited our money and that it is growing. At an exponential model of 2.4%. So if we write our model, that tells me that P of t equals the initial amount, P sub 0, e to my growth rate, 0.024 t. And it is growing, so that's a positive growth rate, 0.024 t. And I know it's exponential, so I know that this is the form my function will take. If I started out with say $5,000, and I want to know how long will it take to reach $10,000. We learned how to work with that in our last video. So I want you to go ahead and pause the video, solve this for t, and then start the video again. So I see that the 5,000 is my initial amount. I'm looking for t, how long will it take? And the ending amount, P of t, is 10,000. So I plug all of those numbers into my equation in the appropriate spots, and I solve for t. And by now, hopefully, you've done enough of these. You know you divide by 5,000. 10,000 divided by 5,000 is 2. Take the natural logarithm on both sides. And divide by the rate. And we plug that in on our calculator, and we see that we get natural logarithm of 2, close parenthesis, divided by 0.024, and we get 28.88. So it would take 28.88 years to double my money at that interest rate. Now, what we're going to look at is that I started with 5,000 and I ended up with 10,000. So what I did here was I doubled my money. And notice that my first step was to divide the 10,000 by the 5,000, and that gave me a 2. So if I started with $1 million, and I wanted to know how long it took me to get to $2 million, my first step would be to divide by the million. And I would end up with 2 equals 0.024 t. So what we're seeing here is that it doesn't matter how much I started with and how much I ended up with if I'm doubling my money every time. I will always divide, and I will always end up with a 2 on the left-hand side of the equation. And then, of course, from there, the work will be the same, and I will end up with the exact same time. So this is what's called the doubling time, because after we did our division, our ratio, our comparison of P of t to P sub 0 was 2. So I can do this even if I don't know an ending amount or a beginning amount. So if I said, what is the doubling time with a rate of 5.3% interest? I have already jumped into the problem after I have divided by the P sub 0. And because it's a doubling time, that tells me P of t over P sub 0 is equal to 2. And my interest rate is 5.3, and it is a growth rate, so it is a positive 0.053 t. And then I can solve using my natural logarithm, divide by my interest rate, and I get t is equal to 13.08 years. And it's a much quicker time because we had a higher rate. So we can see that we don't have to know our beginning amount or our ending amount. All we have to know is the ratio of those two things. Let's use that same concept with the concept of half-life. The half-life of a substance is the amount of time it takes for the substance to decay to 1/2 of its original amount. The half-life of a substance is the amount of time it takes for the substance to decay to 1/2 of its original amount. So half-life relates to things that are decaying, not growing. And notice that it's the amount of time. So a half-life is a time. Let's say that I know that the half-life of carbon-14 is approximately equal to 5,750 years. All living things are made of carbon, and they have an isotope called carbon-14 that as soon as that living thing dies, the carbon-14 starts to decay at a known rate. And it's known that its half-life is 5,750 years. What we want to do is find the decay rate of carbon-14. Now remember, the 14 here is part of the name. It doesn't have anything to do with the math that we're doing. So what we're going to do is we're going to write an exponential model. And remember, our exponential model looks like this. But we're going to be looking at this after we have already divided out the p sub 0. We're looking at the ratio or the comparison of the starting amount to the ending amount. What we know is our time. Remember, half-life is time. So we know our time is 5750. All right, so we know our time is 5750. We also know our ratio, P of T, our ending amount compared to our beginning amount. Because this is a half-life, the ratio between the ending amount and the beginning amount is 1/2, or 0.5. And what we are trying to find is the rate. So I'd like you to go ahead and put the 5750 in for T, the 0.5 in for P of T over P sub 0, and solve for K. Pause the video, do that, and then turn the video back on. All right, so we have 0.5 equals e to the k, because that's what I'm trying to find, times 5750. So as always, when my variable is in the exponent, I take my natural logarithm, and that gives me the 5750 times k, and now I can divide. And I plug that in my calculator. ln 0.5, close my parenthesis, divided by 5750 equals, and on my calculator it's saying negative 1.2 e to the negative 4. So let's remember what that means. That e to the negative 4 means negative 1.2 times 10 to the negative 4 power. So that means move the decimal to the left 4 places. So k is negative 0.00012. So we were asked to find the decay rate of carbon-14, and we see that that decay rate is, the k is negative 0.00012. Now saying decay rate implies it's negative. So if I say the decay rate, I just say the decay rate is 0.00012, because the word decay implies that it's negative. Let's go ahead and write an exponential model. For carbon-14. And we don't know our starting amount, so we're just going to call it P sub 0. So we have P of T equals our starting amount, P sub 0, E, and we just found out K was negative 0.00012, and we have our T. So that's an exponential model for carbon-14. And we can use this specifically for carbon-14. We can use that model to find out how old things are. So if I know that the Lascaux cave paintings have lost 88.5% of their carbon-14, and I want to know how old are the paintings. Now, I would encourage you, after you watch this video, I would encourage you to Google the Lascaux cave paintings. They are some really fascinating, amazing paintings found inside of a cave in France that are just astounding. So take a few minutes and Google those and look at some of those images. But let's go ahead and go back to the math here. The Lascaux cave paintings have lost 88.5% of their C14. So that means that they have 100 minus 88.5, which is 11.5% of their original carbon-14 remaining. That means the comparison between how much they started with originally and how much they have now is 11.5%. And remember that that comparison, that ratio of how much they have now, P of T, to how much they started with, in this case, is the 11.5%. So writing that as a decimal, we have 0.115 equals E, and because we have carbon-14, we know we have a decay rate of negative 0.0012. And once again, how old means that we are finding T. You go ahead, pause the video, and solve this equation. And we see that we are taking our natural logarithm we are dividing and we will end up with negative 0.00012. We will end up with approximately 18,000 years old. So scientists know by carbon-14 dating that the paintings inside the Lascaux cave are approximately 18,000 years old. So what we learn on this lesson is that sometimes we don't know the original amount or the ending amount, but what we know is the ratio or the comparison of those two things. And we can use that to solve problems with doubling time, half-life, or even some other percentage. In our last lesson on exponential models, we're going to look at finding an exponential model when we don't know a rate, but we can find it by comparing